Okay, Chem 1110 students, now we're going to look at the second part of Chapter 11. In the beginning part, we talked about various gas laws that people had discovered. Boyle's law, Avogadro's law, Charles' law, Graham's law, effusion and diffusion, etc. And what was found, this work was done around the same time to describe behavior of gases, and then it was realized that we could actually combine them into something that's called the ideal gas law. And so that's where we're going to go with this chapter. We're going to start talking about the ideal gas law. So all of those gas laws could be combined into one general equation. So you had Boyle's law, which said that the volume was inversely proportional to the pressure. Charles' law that said the volume was proportional to the temperature. And Avogadro's number that said, or law that said the volume was proportional to the number of components or molecules that were in a sample. And when you put those all together, you see that the volume is proportional to the number of moles times the temperature divided by the pressure. And once again, we can turn this into an equality by including a proportionality constant. You can see we just put an R in there to make it equal. Then we arranged it to PV equals nRT. And that R is a proportionality constant, and we call it the gas constant. So the ideal gas equation shows you the relationship between all four of the variables: the pressure, the volume, the number of moles, and the temperature. So there's some important things to know about how well this applies. Applies well to a hypothetical gas sample whose pressure, volume, and temperature behavior is accurately predicted by the ideal gas law. So let's look at the gas constant. It's a proportionality constant, as you can see, and there are a lot of values for it depending on the units that you use for your pressure and volume and temperature. And in our work, we are going to use a numerical value of 0.08206 because our volume will be in liters, our pressure will be in atmospheres, our temperature will be in degrees Kelvin, and we will use moles. So the other thing that's important to know about are standard temperature and pressure, which are some special conditions used in many ideal gas law problems. So the pressure is 1 atmosphere, and once again, think about that in terms of something that was readily attainable by early researchers. The temperature is 0 degrees C, which is 273.15 Kelvin, but 0 degrees C is the freezing or melting temperature for water, so an ice bath would allow you to achieve this standard temperature. And the volume for 1 mole of an ideal gas is 22.4 liters. And you can just calculate that out with 1 mole using our value for the ideal gas constant and the standard temperature and pressure. You get 22.41 liters for 1 mole of a gas. So here's a problem that we will go through. This is just looking at it at 25 degrees C, which is room temperature. Okay, so we can do some other things with the ideal gas equation. With a little algebraic manipulation, we can solve for various kinds of variables, but one of the ones we're interested in is density. And so here you have PV equals nRT. And we know that if you have mass over volume, that is equal to density. Well, we know we can rearrange this to put N over V. And if we do that, that means that is equal to P divided by RT. And we can add the molar mass in there. Molar mass times number of moles is pressure, but we're putting it on both sides of the equation. And so we see that density is equal to pressure times the molar mass divided by RT. And here's an example of a problem we could do where that's a useful thing to understand. So actually I had a couple of problems there. Okay, so we know that the ideal gas constant works for gases in an ideal state, but of course we're going to apply it to real gases. We want to look at what that does to have some deviation from ideal behavior. And this little chart just shows you ideal gas would give you a volume of 22.41 liters. That's the first purple bar. Argon, which is a noble gas, is pretty darn close, but chlorine deviates. Hydrogen, helium, and nitrogen and neon all look pretty good, but ammonia deviates, as does oxygen. And the reason for this is that at high pressures, molecules are actually close together and their individual volume for the individual molecule starts to become significant. And at low pressure or low temperatures, the molecules are moving slower and therefore any intermolecular forces become more significant. So when we want to apply the ideal gas law, the best condition is low pressure and high temperature. All right, so here's one other law and behavior of gases that we want to investigate. And this is what happens when you actually mix gases. And so you maybe have some diffusion going on here. So if you put two or more gases in a container, each gas behaves as though it's there by itself. Because you remember, these molecules don't interact. They're moving all the time and they don't interact. And so if you had 1 mole of nitrogen gas in a 5-liter container at 0 degrees C, you can calculate the pressure, putting in that value for the ideal gas constant of 0.08206, and you get the pressure is 4.48 atmospheres. If you added a mole of oxygen to the same container, you also would get 4.48 atmospheres. It's an additional 4.48 atmospheres. So the total pressure you would find would be 8.96. The two pressures for the individual gases just add up. And that's what Dalton's law of partial pressures says, is that the pressure exerted by a gas mixture is going to be the sum of the partial pressures. So the pressure is the sum, that's that Greek letter, epsilon, which stands for sum, of the individual pressures. And here, once again, we just have this little diagram where we have the same volume and we've added other gases like we discussed in the previous example. So each component exerts a pressure independent of the other ones, and so we have another picture that shows they're combining and that they are very additive. And so we have an example problem here that we will do in class. Now we're going to look at mole fractions. And that is a relative amount of components in a gas mixture. So it's like a regular fraction. If you put a cup of sugar and a cup of flour, it's a 50-50 mixture, or each can make up 1/2 of the mixture. Except for here, we're going to be looking at number of moles. And so the mole fraction, it's chi. It looks like an X. For some component I is going to be the number of those molecules for I in terms of a mole divided by all of the moles that are present. and this is specified here on the right hand side of the slide. There's three things you have to remember when you go to use mole fractions. The first is that the mole fraction of a mixture, of any component in the mixture, has to be less than 1, and that the sum of all the mole fractions have to equal 1. And remember, mole fractions are dimensionless. It's like a regular fraction. Okay, so a mole fraction can also be determined using pressure if you don't know the number of moles, because the number of moles and the pressure are proportional to each other as long as you know the temperature and the volume. Because remember, the pressure is due to the collisions of the molecules as they hit the wall of the container. And so chi, or the mole fraction for this component I, is equal to the pressure of I over the total pressure. And you can also say that chi times that total pressure, or the total number of moles, is going to equal to the number of moles for I. Same thing works for pressure. And I have an example here we will do in class, and that's the end of chapter 11.